And here comes the part where we need to check the statistical quality of our random numbers generated by the random number generation scheme. So let's just say we have used the linear congruential method to generate a sufficiently long sequence of random numbers. We need to check the uniformity and independence properties on this random number sequence so we can be sure that this sequence conforms to these two properties. Now we use frequency tests to check the uniformity property. We can either use a Kolmogorov-Smirnov test, which is much more powerful test compared to chi-square test, or we can use a chi-square test, which is less complex in computation. So Kolmogorov-Smirnov is much more powerful. However, chi-square test requires less computation, a less amount of computation to perform the test. So chi-square test is faster. However, Kolmogorov-Smirnov test result is much more powerful. Now we use autocorrelation test to check the dependence relation between numbers. Also, the desired autocorrelation would be 0. We are going to focus on the frequency tests for this week, and the next week we are going to talk about the autocorrelation tests. Okay, so what is the hypothesis test for the uniformity property? Now, in the formal procedure, on the formal statistical procedure or formal statistical tests, we are going to have a sequence of random numbers, and obviously it is better if you have a longer sequence. The hypothesis will be as follows. The null hypothesis will be indicating that this random number sequence is uniformly distributed between 0 and 1, and the alternative hypothesis says the otherwise. And in the end of the hypothesis testing procedure, you know that we either reject the null hypothesis, which means rejecting null hypothesis means proving that the alternative is true, or we fail to reject null hypothesis. Okay, so rejecting null hypothesis means that alternative hypothesis is true, but if you fail to reject the null hypothesis, this means optimistically the null hypothesis can also be true. Please notice that there is no way of proving that the null hypothesis is true. So you can never prove null hypothesis. If you fail to reject null hypothesis, optimistically you can say that it is true. If you fail to reject the null hypothesis, that this means there is no evidence of non-uniformity. So there is not enough statistical evidence to disprove the uniformity property. This means we can optimistically believe that the null hypothesis is true. Similarly, if we are going to perform a hypothesis test for the autocorrelation, then we are going to have a sequence of random numbers again, and the null hypothesis will indicate that the random numbers are independently distributed, and the alternative will state that the random numbers are not independent from each other. Again, we either reject null hypothesis or fail to reject null hypothesis. If you reject the null hypothesis, then this means the random numbers show a certain dependence structure, and there's a statistical proof for that. And if you fail to reject null hypothesis, this means you can optimistically say that the random numbers seem to be independent, and still this does not mean that they are certainly independent, but you can optimistically believe in that. And this means if you fail to reject both null hypotheses in the uniformity and independence test, you can say that you can use the random numbers as a raw material for the simulation procedure. Now, we need to revise our knowledge on hypothesis testing a little. In hypothesis testing procedures, there are two types of errors. The first type of error, type 1 error, is called rejecting the null hypothesis while the null hypothesis is true. So, for example, for the uniformity test, suppose that the null hypothesis is true, which means the procedure produces uniformly distributed random numbers, but the sample that you have may have some extraordinary numbers by chance, and the testing procedure that you have developed may reject that fact. Statistically, it may believe that the sample is not uniform, and this is called type 1 error. So while the random numbers are actually uniformly distributed, it is possible that your test procedure can reject that fact and statistically prove that it is non-uniform. And this is called type 1 error. And the type 2 error is what? Type 2 error is failing hypothesis while the null hypothesis is false. This means actually your random numbers generated by the method are not uniformly distributed, actually. However, again, that it is generated in the sample are by chance showing a uniformity property. It is possible. So your testing procedure may fail to reject the null hypothesis in that case. Type 2 error is failing to reject the null hypothesis while the null hypothesis is false. So we have these two types of errors, and we represent these errors with an alpha and beta probability. Now, having a type 1 error is what? It's a conditional probability, while the null hypothesis is true, rejecting null hypothesis. So the probability of this is alpha. And of course, in every statistical hypothesis testing procedure, there will always be a type 1 error. Okay? I mean, if you are developing a procedure where you reject null hypothesis based on a criterion, such as p-value criterion, if you are developing such a method, there will always be a probability of type 1 error, and that is a conditional probability denoted with alpha. And the probability that you fail to reject null hypothesis while null hypothesis is false is called beta. And in the statistical hypothesis testing procedure, both of these errors are possible to happen. Now, statisticians consider type 1 error to be more serious than type 2 error, basically. We would like alpha to be as small as possible, and that alpha is called the significance level in a hypothesis testing procedure. But there is this unfortunate situation. If you reduce alpha for a given sample or given statistical testing procedure, if you reduce alpha, type 1 error, then this increases type 2 error, okay? So basically, if you are going to make your decision based on a p-value, and if you, for example, fail to reject the null hypothesis with a p-value that is greater than alpha, and you can reduce the probability of type 1 error, of course, but that is also going to increase your type 2 error, okay? So these are conflicting objectives. So for a given sample size, if you reduce type 1 error, it increases type 2 error, or vice versa. If you reduce type 2 error, then it will increase type 1 error. Now, the way that we need to choose the type 1 error or the significance level of the hypothesis testing can have these small rules. So if you have a small sample size, for small sample sizes, you can use a significance level that is equal to 0.10. Or for moderate sample sizes, you can use 0.05. And for large sample sizes, you can reduce alpha to 0.01. So what does that mean? If your sample size is large, then reducing type 1 error, of course, it is going to increase the probability for type 2 error. However, the amount of increase in type 2 error is going to be small if your sample size is large. So we should say that every time you reduce alpha, it will increase beta. So just like a seesaw here, if you reduce alpha, it will increase beta. If you increase alpha, it will reduce beta. However, for large sample sizes, enough large sample sizes, even if you reduce alpha type 1 error very fast, it will only increase beta at a small amount. This is for large sample sizes. For small sample sizes, unfortunately, even if you reduce alpha a little, beta will increase so much. Okay, so therefore, it is always better to work with large sample sizes.